Hello all. In this video I want to talk about a math tool that we're going to be using in our next chapter. The next chapter is ultimately going to be about projectile motion. We want to try to see if we can discuss the motion of a projectile, like a ball or a ball kicked through the air or thrown through the air, or a bullet shot through the air, something like that. And in order to talk about the motion of a projectile, we need to first know a little bit about a math tool called vectors. So this video is going to be all about vectors. First of all, before we get into it, let's define what a vector is. It's a sort of a fancy sounding word for something that's not that fancy. It's just a measurement that has both size and direction. So we say this is a measurement with what we call magnitude. That's just a word meaning size. Magnitude or size and direction. So some measurements that you make require both a magnitude, a size, and a direction. Not all do, right? So there's some measurements where direction is irrelevant. So an example of that would be like a measurement of volume. If I have a gallon of milk, there's no direction to it. It's just I have a gallon of milk. It's not a gallon left, or a gallon right, or a gallon north, or a gallon east. It's simply a gallon of milk. But some measurements do require direction, and an example of that would be displacement is a classic example. So what do I mean? I mean, if I tell you that I just went 5 miles, you might want to know what direction I went in, right? If you want to know where I am, I can't just say, oh, I walked 5 miles. I have to tell you that I walked 5 miles east, or 5 miles north, or 5 miles east of north, or I have to somehow tell you what direction I walked in if you want to know where I am. So displacement is an example. Other ones that there's a whole lot of examples, but the other ones that we've talked about are velocity. So you might remember last unit when we had a velocity, we had to decide if it's positive or negative. That's the direction. Is it positive or is it negative? Again, for this chapter, we'll say a certain velocity east or west or up or down or left or right, whatever. And then acceleration as well is a vector quantity. So it requires a direction that if you remember that also, we made positive or negative in our last unit. Okay, so this is a type of measurement with magnitude and direction, and the math behind it, first of all, we represent a vector by using an arrow. So this arrow, that arrow right there could represent a vector. And the length of the arrow, so this length here, indicates the size. I probably should use an arrow there. The length gives you the size, and the arrowhead determines the direction. So that probably makes sense that the arrowhead would give you the direction. So I can represent a vector using that arrow. So for instance, to make it a little bit more interesting, let's imagine that Buck the dog takes a trip. So this is Buck. Floppy ears and a snout, and that's his tail. So here's Buck. And he takes a trip, and we want to know what sort of trip he takes. So maybe he starts from this location right here, there. That's his starting point. And maybe he goes 3 miles east. And then he turns and he goes 3 miles south, and then he goes 2 miles west, 2 miles south, and then he goes a mile east. So here's his trip. Or sorry, this is west. So 3 miles east, 3 miles south, 2 miles west, 2 miles south again, and then 1 mile west again. And so here's his end point right here. And we might want to know So first of all, these arrows, each arrow indicates a leg of the trip. So there's 1, 2, 3, 4, 5 different vectors here. Well, the first thing you might notice, what's his overall displacement, right? What's the overall displacement? And it shouldn't be too hard to figure out that his overall displacement is just from the start point to the end point, this arrow. So this arrow here represents the overall displacement from the start to the end. Okay. Now, this arrow, this red arrow here, does not represent the total distance. Right? The total distance is 3 plus 3 is 6, 7, 8, 9, 10, 11 miles. But this is the displacement, right? The direction, when we're talking about displacement, is relevant. So this is the overall displacement. And sometimes we call this arrow, when you combine a bunch of vectors into one, we call it the resultant. So you'll see me use the word resultant, or you'll hear me use the word resultant to mean the vector that's used to represent a whole bunch of other vectors. So in this case, all of these 5 vectors can be reduced to this one resultant. And the next thing I want to think about is how could we figure out what the resultant is? In this case, hopefully you see that it's not too hard, because I went 3 miles east and then 3 miles west, right? There's 2 miles west and another mile west. So the east-west cancel out. I have a total of 3 miles east and 3 miles west. So the only displacement is south. And how much south did I go? Well, I went 3, 4, 5. So the displacement here, the resultant, in this case, we would say is this resultant here is 5 miles, and we need a direction south. Okay, so get used to this whenever we're looking for a vector quantity. So if I ask about displacement, you need to have that direction. That's important. That's an important part of the vector. If you don't give the direction, you're not giving the vector, you're giving something else. So 5 miles, and in this case it's south. We're not anymore in the world of positive, negative. It's now north, south, east, west. So that's a sort of a brief explanation. And so we've actually used a little bit of vector math already. It's pretty straightforward, so you probably didn't even realize we were doing it, but let's get into that. But the first bit of vector math I want to go over is adding or combining vectors. Adding vectors. And we did a little bit of that here. The most straightforward cases, when there are 2 vectors pointed the same way, you just add them together. So we had 3 south and 2 south gave us 5 south. So the most straightforward way of combining vectors is if they're pointing in the same direction, parallel. And if they're parallel, all you do is add them. So if I had 3 plus 4, I get 5. Very straightforward. And note that I'm making the arrow lengths represent the magnitude, right? So this 3 is shorter than the 4, and the 5 is longer than the 4, because the length is supposed to tell us something about how big the vector is. So that's a pretty common sense case right there. Adding vectors when they're parallel. The second one that we did in that video, or in this example up here, was when we saw that when the vectors were pointed opposite, we subtracted them. So 3 minus 2 minus 1 was 0. So the other case is when they're what we call anti-parallel. Anti-parallel just means pointed opposite directions. And when they're pointed opposite directions, we subtract them. Again, pretty common sense. So if to use my example up here, if I had 3 plus 4, now they're opposite. You can see how they're pointing in opposite directions. What do I get? I get 1. Which direction? Well, the 4 is bigger than the 3, so I'm going to make it to the left here. So now my resultant between 3 and 4 when they're opposite is 1, and in this case, the way I've drawn my arrows, it's 1 directed to the left. Okay. The last way we're going to go over for combining vectors is the case, and we didn't see this in the previous example, but what would you do if you had vectors that were perpendicular? Right? So what if I had, I'll jot down here, what if I had 3 and 4 like this, such that this right here is a right angle? What would my resultant be now? It may be, first of all, you can hopefully see that the resultant, I'm going to draw the resultant. The resultant, again, is from the start to the finish, so it's this line right here. That's the resultant. I'm going to put an R in there for resultant. And maybe you can see that the resultant is the hypotenuse of this right triangle. So maybe you can see that we're going to have to use the Pythagorean theorem. So when it's perpendicular, we use Pythagorean theorem. In other words, R here, my resultant is going to be the square root of 3 squared plus 4 squared, which is the square root of 25, or 5. So my resultant now is 5. Now I'd have to give a direction here, and the direction that I would give, in this case, I would say this angle here, I'd like to give that angle. So I'm going to call that angle there, I'm going to call that angle theta. Hopefully that symbol doesn't confuse any of you. Hopefully you've seen it in math. This is the Greek letter theta. Theta. And it's used frequently in math and physics to represent an angle. So that's angle theta. So what if I wanted to know what theta is? How could I figure it out? Well, giving the angle of this result and figuring out theta is a little bit of math that I'm hoping that you've all learned, although it's possible it's not fresh in your minds. And that's something called SOHCAHTOA. SOHCAHTOA. So the way this works is S stands for sine, and the sine of theta equals the opposite, which is 4. 4 is opposite from theta, over the hypotenuse, which is 5. The C stands for cosine. Cosine is equal to the adjacent. Adjacent means next to, adjacent over the hypotenuse. And the T in TOA stands for tangent. And tangent is opposite, 4 over adjacent, 3. You can use any of these angles to find this, or you can use any of these. They're called functions. They're called trigonometric functions. You can use any of these trig functions to find theta. I'm going to go ahead and use tangent this case. I'm going to use this one right here, and I'm going to say tangent theta, the tangent of theta right here is O over A, opposite over adjacent. So that's the tangent of 4 over 3. Actually, why don't I'm going to go ahead and get my calculator here. So what I can say is tangent theta equals 4 over 3, but how do I get theta? Well, I have to, in order to get the theta, this stands for the angle, right? That's what I'm trying to figure out all alone. I've got to take the opposite of tangent, which is called the arctangent of both sides. So I say theta equals the arctangent of 4 over 3. This calculator is a little bit different than your calculator, and I think the way I have to do this is I think I have to put in the arctangent first. So I think if I hit this inverse button, I'm going to get tangent to the -1. That's what your calculator will say. Tangent to the -1 means arctangent, so I think on this one I hit that, and then I do 4, or maybe I don't, 4 divided by 3. Oh, now I have to do the arctangent, I think. So there we go. So we got what? What did we get? What was the angle? 53 degrees, 53.1 degrees. Make sure that's right. Yep, 53.1 degrees. And now I can give the vector. Now I can say the resultant here is 5, whatever this was, miles, inches, meters per second, miles per hour, whatever it was. I can say 5, and then I can give this direction. So I could give this as a 53 degree angle, 53.1 degree angle. if this were like on a compass, I could say 53.1 degrees. And how would I give this angle? I would say here's south. I would say east of south. Right. So if this were positions on a compass, I'd say 53.1 degrees east of south. So that's a little bit about how to combine vectors when they're perpendicular. If this SOHCAHTOA business is not clear to you, if you haven't learned it or you don't really remember it well, and if this didn't help that much, you're going to have to make a point of asking in class or coming to see me for extra help. So that's the first little bit. I want to move on to something else in just a minute here, but that's the first little bit about adding or combining vectors. So taking two vectors and making them into one. The next bit that I want to talk about is essentially the opposite of that, which is splitting vectors up. And the fancy word for splitting vectors up is vector resolution. So vector resolution is a fancy term for taking a vector and splitting it up into pieces. So splitting a vector. So why would you do this? Well, let's imagine I have a vector, and so I guess I'll stick here with the black. So I have a vector. Let's say I tell you that I move, I'm going to give you a displacement vector again. I go, let's see, we'll make it 6 miles. I say I move 6 miles, and I tell you that I move at an angle of 30 degrees north of east. So that's how I would give this angle. I'd say 30 degrees north of east. So east is to the right, and I'm going 30 degrees up from that. And you might wonder, or I might wonder, if I went 6 miles 30 degrees north of east, how far did I go east? In other words, how much of this vector is pointed in the easterly direction? You might also want to know, how far north did I go? In other words, how much of that 6 miles was in the north direction? And so these are what we call the components of the vector. These are what are called vector components. And this component, the side-to-side component, is usually called the x component. Sometimes you'll hear me call this the horizontal component. And this is the y component, sometimes called the vertical component. So the x and y components. Component is just a fancy term meaning a piece. A component is a piece of something. So we're splitting this 6 mile vector into a certain number of miles in the x direction, which is east in this case, and the y direction, or vertical direction, which is north in this case. All right, so how do we do that? How do we figure out what these components are? Well, again, we're going to have to use our SOHCAHTOA. SOHCAHTOA. So I have the angle now. I'm given the angle theta. And if I'm looking for the x component, I'm looking for this side right here. And that side is adjacent or next to the angle. So I have the hypotenuse. 6 is the hypotenuse. Right here's my right triangle. I've got the hypotenuse, and I'm looking for the adjacent. So I'm going to use cosine for this one. I'm going to say that the cosine of the angle, which is 30 degrees, is equal to the adjacent. That's what I'm looking for. That's x. That's what I'm trying to find, over the hypotenuse, which is 6. And so I can say that x equals 6 cosine 30 degrees. And so now I take out my calculator and I type in 30, and I hit the cosine, and that equals this business. So that's cosine 30, and then I have to multiply that by 6 times 6. And that gives me about 5.2, 5.19. In other words, this right here is 5.19 right there. So if I went 6 miles 30 degrees north of east, I've gone 5.19 miles east. So what about the y component? How far did I go north? Well, let's think about the y component here. This component is opposite from the 30-degree angle. It's away from, opposite that angle, and I've got the hypotenuse, so I'm going to go ahead and use sine now, right? And I'm going to say, I'll do it up here, I'm going to say that the sine of 30 degrees, sine equals opposite, that's what I'm looking for, that's the y, over the hypotenuse, which is 6. So y equals 6 sine 30 degrees. Take out my calculator. 30 sine times 6 equals 3. So I can see now that in this case I've gone exactly 3 miles north. So 5.19 miles east and 3 miles north in this case. So again, using SOHCAHTOA, hopefully you're familiar with that again. So now I've got the components of our vectors. And there are numerous times where this comes in handy. I'm going to show you one way this comes in handy, and this will be the last little bit that we'll do in this video. Let's imagine I had two vectors that I have to combine. Let's say I have a vector that's, let's say that this vector is 5 miles east. We'll imagine I'm taking another trip. 5 miles east. And then when I get to this point, I go at an angle south of east. So I go like this. And I move, let's say, 4 miles south of east. So what's my resultant? Well, again, my resultant is start to finish. Here's my finishing point. And it's hard to draw this line very straight. Let's see. That's slightly better. So here's R. It's my resultant. How do I find this? Well, let's go back. I'm trying to combine these two, right? So let's go back to our rules for combining vectors. See if we can use any of those. Okay, well, are they parallel? No, they weren't parallel. Are they anti-parallel? Nope, they're not pointing opposite directions. And then, so what about the Pythagorean theorem? Well, the Pythagorean theorem works when the vectors are at right angles, when they're perpendicular. And if I look, this isn't perpendicular. Okay, so actually, let's give an angle to this so we can finish the problem. What if I tell you that this angle right here, what if I say that that's, I don't know, let's call that 25 degrees. So it's 5 miles east and then 4 miles at a 25-degree angle south of east. That means that this is not a right angle. And if this isn't a right angle, I can't use the Pythagorean theorem. So how am I going to combine these two vectors? Well, here's where I can take this vector, the 4-unit vector, and I can split it into east. And I can split it into east and south components. So I can go ahead and split this guy into its east and south components. And I'll go ahead and do that. I'll say that this piece right here, the easterly component, I'll call X, and the south component I'll call Y. So X is going to be, I'm going to skip a step here, I'm doing the same thing I did up here, right? Cosine of the angle, and I'm going to say that X equals 4 cosine 25. Like I did up here. This was 6 cosine 30, now I'm doing 4 cosine 35, and I'm going to say Y, I'm going to use the sine, is 4 sine 25. Get out my calculator and say, so 25 cosine times 4 is 2.6. That's 2.6 miles east, so this is 2.6. And then we'll do the y here. Say 25 sine times 4 is 1.7. I'm going to round that to 1.7, so this is equal to 1.7. 1.7. And now what I can do, since I know that this is a right angle, now I can go ahead and erase this. Okay? I've split that vector, the 4-unit vector, into its two components, so I can go ahead and get rid of it. And now I've got one big right triangle, right? Let me get rid of that as well. So now I've got one big right triangle. And the overall east part of this right triangle is 5 plus 2.6, which is 7.6, and the overall amount south is this, 1.7. And now I've got a right triangle and the legs are 7.6 and 1.7. So now if I want to know r, I can say r here, r is going to be the square root of 7.6 squared plus 1.7 squared. And then we can just go ahead and do that. We'll say, let's see how we do this. We'll do 7.6 squared plus 1.7 squared equals 60, and then we'll take the square root of that. Where's my square root? Oh, there it is. So this is 7.78 equals 7.78, and whatever this was, miles. So this equals 7.78. But we're not done, right? Because we've got to give this angle theta. We've got to figure out what the angle is. Again, if it's a vector, you need to know the angle. So once again, we're going to use our SOHCAHTOA. And I'm going to go ahead and use tangent again. I'm going to say that the tangent of theta is opposite. So remember SOHCAHTOA, I'm using tangent, T-O-A. Tangent is equal to opposite over adjacent. So here's the angle. The opposite is 1.7 over the adjacent was 7.6. And so now I can say theta is going to be the arctangent. So I'm going to do 1.7 divided by 7.6. And then I have to take the inverse tangent, the arctangent of that, and I get that that's an 82.5 degree angle. So this is 82.5 degrees. So now I can give my resultant vector. And to think about it, this tells me if I took this trip, I started here and then I went here and I called back home and I wanted to tell somebody how to get to exactly where I was, this is what I would say. I would say, all right, if you want to find me, you need to go 82.5 degrees south of east, and then you need to go 7.78 miles. And if you move 7.78 miles, 82.5 degrees south of east, you're going to get exactly to me. That's the way the vector works. Okay, so that's it for now. That's a fair amount of information. We went over how to add vectors and then how to split vectors into components. A fair amount of information, but we'll be practicing it next class.